The device was classified as a limpet mine. Its function was simple hull penetration and disabling. Design goals prioritized reliability over spectacle or complexity. The weapon was intended for controlled underwater attachment. Engineers defined consistent adhesion as the primary requirement. Mines needed to cling to steel under fouling. They needed to cling in cold harbour conditions. They needed to cling despite currents and silt. Magnetic fixation was selected after comparative assessment of methods. Permanent magnets offered silent, maintenance-free holding force. Electromagnets were rejected because they required external power. Mechanical clamps were rejected as noisy and cumbersome underwater. The casing adopted a shallow domed profile for stability. This shape reduced drag during diver transport underwater, and it also reduced leverage forces acting on securing magnets. The outer shell used pressed steel of standard gauge. Surface finish remained deliberately rough and utilitarian. No polishing was applied beyond corrosion control requirements. Paint schemes emphasized low reflection in torchlight conditions. Color selection was irrelevant underwater, but useful ashore. Internal volume allocation followed strict spatial partitioning rules. Explosive filling occupied the majority of lower cavity. Fuse components occupied the upper central region. Safety interlocks and arming devices occupied peripheral recesses. Explosive choice prioritized stability during prolonged storage. Cast explosive compositions were favored over more sensitive fillings. Standard naval explosives simplified procurement and documentation chains. Filling temperature limits were documented for each production batch. Charge geometry used a modified shaped charge arrangement. A conical or dish-shaped cavity faced the hull. A metallic liner focused energy into a concentrated jet. Jet formation parameters were derived from plate penetration trials. Standoff distance proved critical to performance consistency. Direct contact reduced jet formation and wasted potential. Excessive standoff dispersed energy and reduced perforation capability. Engineers introduced a built-in spacer ring accordingly. Spacer thickness matched calibrated optimum for typical hull plating. Additional variants allowed for paint layers and fouling. Fouling thickness surveys were conducted in British-controlled harbours. Collected data informed tolerance bands for standoff design. The magnet arrays were arranged symmetrically around the central cavity. Each magnet sat within a recessed pocket in casing. Recessing reduced risk of impact damage during handling. Magnets were secured with non-magnetic fasteners and resins. Pull strength was measured on representative steel plate samples. Tests were conducted in dry and submerged conditions. Biofouling simulants were added to evaluate degraded contact surfaces. Minimum acceptable holding forces were defined in official tables. Early prototypes demonstrated inconsistent adhesion on curved hull sections. Contact points concentrated near the magnet edges under curvature. This concentration reduced effective gripping area and reliability. Designers adjusted magnet shape to tolerate moderate curvature. Later models included flexible backing plates under magnet groups. These plates allowed slight articulation under external forces. Articulation improved area contact on irregular ship hulls. Articulation also absorbed minor impacts during diver placement. The fuse system combined time delay and hydrostatic elements. Time delay mechanisms used clockwork with corrosion-resistant components. Springs and gears received protective coatings against saltwater intrusion. Fuse housings incorporated gaskets to resist low-level leaks. Clockwork units were factory set to standard delays. Field personnel were not authorized to adjust internal timing. External selectors allowed discrete delay options via calibrated cams. Available delays supported synchronized attacks on multiple vessels. Hydrostatic switches ensured arming occurred only below defined depth. Shallow water handling represented a significant safety concern. A diaphragm or bellows responded to ambient water pressure. Movement of this element released an internal mechanical block. Blocks prevented firing train completion while at atmospheric pressure. This arrangement reduced risks during storage and deck transport. Only sustained submersion beyond threshold activated the arming pathway. Designers preferred passive hydrostatic systems over active electrical solutions. Multiple safety layers existed between storage and detonation. A primary safety pin locked the external arming handle. Secondary interlocks immobilized striker components within the fuse body. Some variants employed shear wires calibrated to operational shocks. Standard handling drills required visible confirmation of safety devices. The pins were tagged with clearly printed identification markers. Colored flags allowed rapid status checks in low light. Missing tags triggered immediate reporting under standing orders. Manufacturing followed existing ordnance plant process structures. Casing pressings were produced on general-purpose forming presses. Dies were designed for rapid change and minimal downtime. Inspection gauges verified correct curvature and flange dimensions. Welded seams underwent non-destructive examination using die penetrance. Selected batches additionally underwent radiographic inspection for reliability. Imperfections exceeding specified tolerances led to rejection. Rejected shells were sectioned and used for training samples. Explosive filling lines operated under strict temperature control regimes. Heated kettles maintained casting compositions within narrow limits. Operators monitored thermometers continuously during filling operations. Thermometer readings were logged at fixed time intervals. Filled casings were transferred to controlled cooling racks. Cooling schedules minimized internal void formation within explosive blocks. Random samples were drilled for void assessment after solidification. Unacceptable void patterns resulted in disposal under demolition procedures. Magnet production relied on established suppliers of naval components. Suppliers documented alloy composition and heat treatment schedules. Finished magnets were tested individually for pull strength. Marginal units were culled before assembly to avoid variability. Fuse assemblies were produced in specialized small parts workshops. Clockwork modules came from firms experienced with instrument mechanisms. These firms adapted peacetime production lines for military contracts. Abrasion-resistant lubricants were specified for extended storage life. Hydrostatic elements were machined from corrosion-resistant alloys. Bellows units underwent cyclic pressure testing in water-filled chambers. Chambers simulated repeated dives and ascents during operational carriage. Fatigue failures informed revisions to wall thickness and geometry. Final assembly occurred in segregated bays within ordnance factories. Workers followed stepwise instructions issued as standard operating sheets. Each station handled a limited set of tasks only. This reduced complexity and limited exposure to combined hazards. Completed mines proceeded through functional test stations before packing. Mechanical safeties were exercised to confirm correct travel. Timing units were wound and monitored on calibrated test rigs. Sample units were submerged to verify hydrostatic response behavior. Documentation accompanied every finished item leaving the plant. Serial numbers linked mines to component batch records. Any later defect investigation could trace contributing manufacturing steps. Record-keeping followed Admiralty patterns for other naval munitions. Training facilities for divers were situated in remote locations. Scottish lochs provided deep, cold, low-visibility environments. These conditions mirrored anticipated operational harbours in northern waters. Nearby infrastructure allowed discreet accommodation for personnel and staff. Diver selection followed medical and psychological screening standards. And candidates required strong cardiovascular fitness and respiratory capacity. They also required tolerance to cold water immersion. Previous seamanship or engineering experience was considered advantageous. Training syllabuses addressed equipment, navigation and mine handling. Early sessions focused on basic underwater orientation without loads. Later sessions introduced dummy limpet shells of representative mass. Progression moved toward full operational profiles with live equipment. Divers used closed-circuit oxygen rebreathers for stealth operations. These sets produced minimal bubble emissions during underwater movement. Oxygen toxicity risks were mitigated through depth and duration restrictions. Training emphasized strict adherence to established exposure tables. Protective clothing comprised layered wool and rubberized components. Outer suits reduced water flow across the body surface. Hoods and gloves were issued to reduce conductive heat loss. Boot design prioritized grip on slippery, weeded hulls. Weight systems enabled neutral or slightly negative buoyancy control. Weights were distributed to maintain stable swimming posture. Harness systems integrated attachment points for limpet carriage frames. Frames held mines close to the body for streamlining. Approach profiles were planned to minimize silhouette against surface. Divers followed shadow zones cast by hulls and keys. Natural cover reduced dependency on artificial concealment measures. Movement speed remained slow to limit noise and disturbance. Final approaches used fingertip contact along the hull plating. The tactile navigation compensated for severely limited visibility conditions. Divers counted rivet lines and plate seams to determine positions. Pre-mission briefings linked seam counts to critical target areas. Placement drills prioritized secure seating before arming actions. Divers checked for loose scale or heavy fouling manually. If necessary, they cleared minimal areas using compact scrapers. Excessive cleaning was avoided to minimize detectable disturbance patterns. Once surface condition was acceptable, magnets were brought into contact. Divers applied steady pressure until complete seating occurred. They verified firmness by gentle lateral movement tests. Any unexpected movement required reseating before proceeding with arming. Arming procedures followed a consistent sequence under all conditions. The primary safety pins were withdrawn and retained in pouches. Secondary safeties were manipulated according to specific model instructions. Hydrostatic elements required no diver intervention beyond submersion. Time delay selection aligned with exfiltration and coordination requirements. Standard practice avoided minimal delays except under special circumstances. Short delays reduced flexibility in case of unforeseen events. Longer delays allowed multi-vessel attacks within the same harbour. Divers rehearsed emergency abandonment of partially armed devices. Procedures defined responses to stuck controls or damaged casings. Where possible, safeties were restored before withdrawal from target. If impossible, positions and times were reported on debrief forms. Testing programs preceded operational deployment in foreign theatres. Initial trials used obsolete hull sections anchored in sheltered waters. Controlled charges allowed precise measurement of structural damage patterns. Engineers recorded plate deformation, cracking, and complete perforations. Instruments measured shock transmission through internal framing members. These data assisted in predicting secondary equipment damage on board. Pipework, machinery mountings, and shaft lines received particular attention. Expected flooding rates were modelled from observed hull breaches. Subsequent trials introduced more complex environmental variables. Experiments added tidal flow, increased depth, and suspended sediment loads. Divers operated under strict observation from surface safety teams. Film and photography documented attachment behaviour and detonation results. The reports collated observations into formal recommendations for modifications. Some recommendations involved minor alterations to casing contours. Others involved material substitutions to improve corrosion performance. All changes passed through formal approval channels before implementation. Hydrostatic reliability drew particular scrutiny from safety authorities. False arming at shallow depth presented unacceptable operational risk. Engineers recalibrated diaphragms using controlled depth tank facilities. Revised components underwent extended cycling beyond expected service lives. Procurement bodies scrutinized cost per functional unit carefully. Permanent magnets represented the significant cost fraction per mine. Negotiations with suppliers sought volume discounts and stable contracts. And alternative materials were explored when strategic metals became scarce. Competing requirements emerged between ordnance departments and special operations. Standardization advocates preferred limited variants for logistic simplicity. Special operations requested tailored designs for specific mission contexts. Meetings documented points of disagreement and provisional compromises reached. Some proposed designs prioritized minimal bulk for concealed carriage ashore. These versions incorporated collapsible or detachable components for transport. Assembly sequences grew more complex under such design approaches. Complexity increased training burden and potential assembly errors. Other proposals emphasized maximum charge for heavily armored targets. Larger charges demanded stronger magnets and reinforced casings. The resulting units approached limits of practical diver handling. Trials show reduced maneuverability and increased fatigue during carriage. Several alternative adhesion methods underwent limited development phases. Suction-based systems appeared promising on smooth test panels. However, fouling and micro-damage degraded suction performance in practice. Additionally, suction cups proved vulnerable to shear forces from currents. Chemical adhesives were trialled in laboratory-controlled conditions. Viscosity changed drastically in cold seawater during application. Curing times were inconsistent under varying salinity and temperature. Adhesives were therefore relegated to specialized, rarely used roles. Investigation also briefly considered mechanical spikes or penetrating anchors. These devices would bite into hull plating on impact. They posed unacceptable risks of noise and surface damage. Risk of early discovery outweighed theoretical holding advantages offered. Logistic arrangements governed storage and movement from factories to units. Mines were shipped in padded crates with dedicated compartments. Crates included diagrams showing permitted stacking orientations during transport. Shock indicators recorded any rough handling exceeding specified acceleration thresholds. Storage depots maintained magazines at controlled temperature and humidity. Moisture ingress presented corrosion risks to fuse and magnet components. Regular inspections checked for condensation, rust, or damaged packaging. Defective items were segregated and scheduled for evaluation or disposal. Issue procedures required a documentation at every transfer point. As signing officers verified quantities, serial numbers, and condition remarks, discrepancies triggered investigations under existing ordnance accounting regulations. Losses or unexplained damage were reported to higher authority immediately. Safety instructions accompanied each consignment to operational units. Units confirmed receipt and briefed relevant personnel accordingly. Diver teams received both written and oral instruction updates. Changes in procedure were highlighted during refresher training sessions. Operational theatres imposed further environmental and logistical constraints. Warm water harbours affected diver endurance differently from cold waters. Marine growth patterns changed magnet contact characteristics in certain regions. Field feedback described these variations in standard report formats. That reports from Mediterranean deployments described heavy weed accumulation. This weed layer reduced direct steel contact for magnets. Divers compensated by searching for partial clear zones manually. Engineers later adjusted magnet configuration to tolerate intervening layers. In colder northern harbours, ice occasionally formed along hulls. Ice layers disrupted both friction and direct magnetic seating. Some operations were postponed until conditions improved sufficiently. Others required partial ice removal using small hand tools. Administrative correspondence recorded continuing refinement through wartime years. Memoranda traced each incremental change in design or procedure. Numbered amendments attached to manuals summarized these approved revisions. Obsolete pages were removed and destroyed according to instructions. Royal Navy interests often intersected with those of special operations. Conventional naval staff emphasized predictable, controllable weapon employment. Special operations personnel prioritized flexibility for unconventional circumstances. Policy committees balanced these positions during resource allocation discussions. Ship damage reports from Limpet incidents informed future planning. Analysts reviewed flooding sequences and stability changes after detonations. Some hull breaches were sufficient to ground or capsize vessels. Others produced partial disabling, requiring additional follow-up attacks. Data from such incidents fed back into fuse timing decisions. Longer delays allowed ships to clear congested harbour areas. Detonations in channels obstructed subsequent movements for extended periods. To this effect contributed strategically despite limited explosive quantities employed. Post-war evaluations assessed the entire Limpet mine program. Committees examined engineering documentation, training records, and operational summaries. They considered whether future equivalents should follow similar principles. Many core features remained valid under evolving naval conditions. Magnetic adhesion retained relevance wherever steel hulls persisted. Hydrostatic safety remained a robust safeguard against premature arming. Time delay options continued to support synchronized multi-point attacks. Diver deployment methods informed later clearance and sabotage doctrines. Technical lessons outlasted the specific historical circumstances of origin. Manufacturing documentation continued to influence later mine designs. And testing methodologies shaped broader approaches to underwater weapon evaluation. Record-keeping practices established benchmarks for subsequent special equipment programs. Within this framework, Limpet mines functioned as engineered tools only. Their performance depended on consistent materials and disciplined procedures. Diver training, plant processes, and administrative control all interacted. The system remained effective when each component met defined standards.